All right, so let's talk about the sum and difference of cubes, right? Last time we looked at the difference of squares, right? So that meant that each term was a perfect square. This time, what it means is that every term is a perfect cube, right? And a cube is just a term taken to the third power, all right? That's all that is. So let's begin by just looking at the sum of cubes. So unlike difference of squares, where only the difference of squares was factorable, with cubes, the sum and the difference of cubes are both factorable. Okay, so if I'm adding the cubes together, I can factor it. If I'm subtracting the cubes, I can also factor that. But they take on different forms. So this is the form. So the difference in the sum of cubes is basically a formula. Okay, when you have a term like a taken to the third power plus b to the third power, it factors into a plus b times a squared minus a times b plus b squared. Our job is to identify what is that term that got taken to the third power, because that's the value that we're going to use and plug in for a, or that's the value we're going to plug in for b. Okay. And so we'll explain more as we look at an actual example. But whenever you're looking at a sum of cubes, this will be your reference. Okay, you're going to go back and you're going to use this a lot, and then you're just going to substitute numbers into this. All right, but that's the general form of the factored version of a sum of cubes. Okay, now why the SOAP acronym? Because when you are factoring the sum of cubes, there's a lot of different symbols, right? There's a symbol here, symbol here, symbol here. And it's often difficult to keep track of what are my symbols. So that's where the SOAP, or the same, opposite, always positive, comes in. When you have a sum of cubes, it's a plus in between. So that first term is also going to have a plus in between. So that's why we call it same, right? Same. When it's a difference of cubes, you'll see it's going to be minus and minus, all right? But for plus, it's a plus in between the original. So then when you start to factor it, the first sign is going to be a plus. Then you're going to do opposite on the second symbol, right? So the second symbol will be opposite of this positive, all right? That's where we get opposite from. And then the last symbol, or the last sign, is always positive. Okay, and that's where SOAP comes from. So it's same, opposite, always positive. And that's just a way to help you remember what the symbols should be, or what the signs should be in your factored form. Okay, and this also comes like back in the day when you had to memorize this because you didn't have notes, right? So you obviously have use of your notes. So it's not something you need to memorize, but it's something that helps you as you're working through the problem. So that's the sum of cubes. Difference of cubes takes on almost an identical form. It's just that the symbols are different. All right. So now what we're looking at is a cube, a to the third, minus another cube, b to the third. So notice how we still have a and b, a squared, ab, and b squared. The only difference is the symbols have changed. So check it out. Here, now we have minus in between. So a to the third minus b to the third. So guess what? The first symbol is also going to be a minus, right? Same, right? Same. Since the first symbol is a minus, that means the second symbol will be opposite. So opposite of a minus, it's a positive, so it's a plus. And then at the end, it's always positive, right? Always plus b squared. All right, so that's our SOAP. But you can see how the position of where the variables are at are always the same. The only thing that changes is the symbols or the signs, right? So you have a and b in the first factor, a squared, ab, b squared, b squared, right? It's like, it's the same, okay? So let's take a look at how this would work when we're trying to factor out either a sum or a difference of cubes. Okay, so starting with example 1. I want to factor x to the third minus 8. X to the third minus 8, here's what my job is supposed to be, okay? I need to identify what is the a term, what is the b term, all right? So I need to think of it this way. What is the term that got cubed that got me x to the third power? And what is the term that I had to cube so that when I cube it, I get 8? because whatever those values are, they're going to end up being my A value and my B value. All right, so think about this first one, x to the third. What did I have to take to the third power in order to get x to the third? What must the variable have been? Yeah, the variable must have been x. And then what number did I have to cube to get 8? And Furman helped us out. That would have to be 2, right? It's 2. 2 to the third gives us 8. And then obviously it's still that minus sign in the middle, right, in between. So this is a difference of cubes, all right, difference of cubes. So that means it's going to factor into a minus b times a squared plus ab plus b squared. Okay, where did this come from? This came from the general form from box number 2. All right, so all we have to do is make substitutions. Instead of a and instead of b, what am I going to actually use for a and what am I going to actually use for b? There you go. X will go in instead of a, so I have x minus, instead of b, it's just going to be 2. Hey, look who came to say hi. Hi, everybody. Hi. Okay, you got to go. I'm in the middle of class. Ugh. Let go of the chair, dude. Odin. That's okay. Okay. So let's continue, right? So now notice that the next term that would follow would be a squared, but we know it's not a anymore. It's actually just x squared, right? A gets substituted with x. Plus, now we have ab, right? Well, this actually represents a times b, okay? A times b. So let me use a different color here. It's a product of a times b. So my a term is x. My b term is 2. It's a product of just x times 2 or 2 times x. Okay, we'll clean it up in a bit. And then plus my b term. My b term is 2, and then I want to square that. All right, so ultimately, when I clean this up, this should give us x minus 2, x squared plus 2 times x, or x times 2. It should be 2x plus 2 squared, which is 4. And this here is my factored version, or my fully factored form of a difference of cubes. Okay, any questions on example number 1? So see, our job is fairly simple here. We're just trying to find out what is the a term? Like, what is the term that got cubed? Because that's what we're going to need, right? So it's sometimes just a simple variable, or it's a small number, right? What number got cubed that gave us 8? So you have to think in reverse at the beginning, because then you're going to use that small number for b, and then that variable for a most of the time, and then just plug it into the formula that you already have. All right. Does that make sense so far? All right. So there's example 1. Let's take a look at example number 2. All right, so same process, right? We need to first identify what is being cubed. Oh, how did I know to use it? I looked at the difference here. You look at the symbol in between the 2 terms. If the symbol is a difference, it's always going to be a difference of cubes. If it's a sum, then it's going to be a sum of cubes. All right, so that's how I knew. We'll have a sum of cubes example later on. So I'll use that formula instead. Okay, so I'm going to need to do this twice. I need to find out what got cubed that gave us 8y to the third. Right, what got cubed? Okay, so 2 is part of it, right? Because 2 to the third gives us 8, but we also need the y. There you go, right? So 2y to the third power gave us 8y cubed. Okay, so that means that this entire term represents my A value. All right. And then what is going to be the value that when I cube it gives us 27? Yeah, that's going to be 3, right? 3 to the third gives you 27. And then you still have your minus in between. So guess what my B term is going to be? It's going to be 3. Okay. So you have your notes for reference, right? So you always know, okay, if I'm going to be factoring a difference of cubes, this is the format I need right here. Okay. So this ends up being A minus B, A squared plus AB plus B squared. Okay. And we're just going to go in and do some substitutions. Anywhere we see A, anywhere we see B. Correct. Yes. All right. So let's start substituting. All right. Instead of A, my A term is just 2y. Minus, instead of B, my B term is just 3. All right. When you get to the squaring part, I recommend you start using parentheses. Okay. And here's the reason why. A lot of times, students make the mistake of just writing it as 2y squared. Right. But that wouldn't be correct because your A term is 2y. So it needs to be 2y, the whole thing squared. Right. Because if not, right, imagine you just left it as 2y squared. Then you never squared the 2. Right? You would have left it as 2y squared, where you can see that this eventually will become 4y squared, right? Because the 2 gets squared as well. So anytime you're going to use a larger power, right, and your term like A has 2 parts to it, this needs to be put in parentheses, 2y in parentheses, okay? Plus, right, sometimes it's it's overkill, but it's better to be safe, right? So A is 2y, B is 3, right? So I know that that's going to be the product of A times B. And then lastly, it's going to be B squared, and B is just 3. So we take 3 and we square it. Okay. I know some of you don't do this, and then it shows up later on. Use those parentheses. All right. Use the extra set of parentheses to indicate that the term 2y, the whole thing, is getting squared. All right. So now let's clean it up. We still have 2y minus 3 here as the first term. And here's where the difference in the parentheses matter, because what this is saying 2y times 2y, right? So ultimately that becomes 4y squared. Imagine if you had not used the parentheses, then your answer would look like this. And that happens often, right? And so now you have the wrong expression. Okay, so that's why we use those parentheses, even though, right, it's like we don't like it because it makes it look busy. Plus the product of 2y times 3, so that's 6y. And then plus the last term, 3 squared, which will be 9. So here's my fully factored difference of cubes. Any questions there for number 2? Cool. Okay, let's move on. Let's try example number 3. All right, so with example 3, we don't put 9 squared on 9. No, because my B term, the B term was 3. So we were going to square the 3. So we get to 9. Right? We don't square 9 again. Okay. All right. Sure, we can try example 3 on your own. Let me go ahead. I'm going to pause for now. All right, so let's take a look here. The goal is to identify what term got cubed that gave you 125x to the third, right? So begin with the number at least, right? What number do you think got taken to the third power to give you 125? Yeah, it looks like 5, right? 5 times 5, 25. 25 times 5 again, 125. So 125 comes from 5 to the third. And then in addition to that, we need x, right? So that we get x to the third. So we have identified our a value. Our a value will be 5x. Okay. This time we have our first sum of cubes. Okay. So the signs will look slightly different on the formula. And then we look to identify what was cubed in order to give us 8y to the third. Right. And we can see here, well, we're familiar with 8. 8 comes from 2 to the third. And then we also need y. So 2y to the third power ends up giving us 8y to the third. Okay. So then this ends up being our b term, right? So now our a term has a coefficient and a variable. Our b term also has a coefficient and a variable. So parentheses are going to be really important here. Make sure that you utilize them in order to make sure that you're squaring and you're getting the correct answer. So we begin with the general outline. The general form will be a plus b, a squared minus ab plus b squared, right? So same, opposite, always positive. All right, so now when I do my substitutions here, a is just 5x plus b is 2y. All right, so that's my first term. Second term, parentheses, 5x, and then I'm going to square that, right? A is 5x, so we use the whole thing and then we square that. Minus a, which is 5x, times b, which is 2y. Right, so that's always going to be a product. It's a product of the two terms. And then finally, we add b squared. B squared will be 2y. Make some room. 2y quantity squared. Okay, so now we just need to clean it up a little bit. Nothing to clean up in the first term. That's just 5x plus 2y. All right, but we get 5x squared, which remember, this represents 5x times 5x. So that's going to be 25x squared. Okay, minus the product of 5x times 2y, that ends up being 10xy. And then lastly, the product of 2y, 2y times 2y, which gives us 4y squared. So that would be my final form. Let me erase these just to clean it up a bit. This ends up being the factored form or the equivalent form of the sum of cubes from the beginning. All right, how many of you got that? Okay, which part? Right. Yeah, it's because of the variable. That's right. Yeah. It's because of the variable. All right. Good. Good. Glad you guys were able to identify some of those mistakes. All right. And then lastly, let's take a look at number 4. What do you notice? Is 2 a perfect cube? Is there a number you can think of that if you multiply it times itself 3 times, you get 2? What about 250? Anything come to mind? Same number times same number times same number, you arrive at 250. So are we just done? This one we just can't do it. What did you learn on the first lesson of factoring? Do you see a GCF between 2 and 250? Yeah, okay. So let's start there, right? Since 2 is not a perfect cube, that's a red flag that tells you maybe you need to look to factor something else out before you attempt to do a difference of cubes factorization, right? So you see in every lesson so far, I've tried to bring it back where it's like, okay, we get to a point where it doesn't seem like it's factorable, and it's because we haven't tried GCF yet. But if we try GCF, maybe it reveals itself that, hey, we do have some perfect cubes and we can factor. All right, so let's do that. We decided GCF looks like it's 2. All right, so if we divide both by 2, we get 2 times x to the third minus 125. All right, now when you look at x to the third minus 125, do you identify any perfect cubes now? Yes, we do, right? We can see how in order to get x to the third, we just have to cube x. And in order to get 125, we have to cube the number, we have to cube the number 5. And we have a difference between them, all right? So once again, GCF is what you look to do first, if possible. And then sometimes you'll see that there is a difference of cubes hiding behind it or difference of squares hiding behind it. All right, now this is something that we can factor, right? Difference of cubes. So it's going to be a minus b, a squared plus ab plus b squared. Okay, what's the one number I want to make sure I bring down and not forget because it's part of the original expression? The 2, that's right. So if you need to bring it down right now so you don't forget it, bring it down. All right, now we're going to make our substitutions. X stands for A, 5 stands in for B. So let's go ahead and do all the substituting. 2 times A will be X minus B will be 5. A squared, well, A is just X, so that's going to be X squared. Plus AB, right? A times B, that's going to be 5X, or 5 times X. And then plus, you get 5 squared. So one last time, clean it all up. 2 times X minus 5 times X squared plus 5X plus 25. Okay. Any questions on number 4? So the hint here was find the GCF first. Would it all be in brackets? What do you mean brackets? Yeah. Oh, I see what you're saying. Would it be this? Yeah, it's equivalent. Same thing. They would both be correct. All right, so there it is. Difference of cubes and difference of squares. I'm sorry, difference of cubes and sum of cubes. That's what I meant to say.